sustainability, right? That we all want to be able to make decisions that can have a big impact on the world. We all want to design components and systems that are going to make the world a little bit better place that have real impact. And so part of that is through these concepts of stuff like sustainability, renewability and all that kind of thing. So what I'll talk about, and again, let's continue on our sort of pathway of free-ranging conversation, which I'm 100% open to, is we'll talk a little bit about renewable transportation and some of the energy sort of problems that transportation is part of. And some of the big concepts here are going to be stuff like trying to think about our the environmental tail that goes along with transportation in particular, but even any of the things that we do. The way that regulations can control the way we think about hybrid electric vehicles, mass versus personal transportation, these trade-offs that we all kind of make. So, we want to make sustainable transportation, and this is kind of the way that people have talked about the ideas of sustainable transportation. Obviously, it's not just enough to sort of think about sustainability from a sort of like super global point of view. We all want to experience, we don't want to pay the prices for transportation. So we think about it in terms of natural environment. That's things that probably are what you might think about: oil, air pollution, soil and water pollution, recycling, all this kind of stuff. But also in terms of societal sustainability, like we want to have equity of access for people to transportation services. We want to enhance human health. It's not, there are concepts like environmental justice and stuff like that, where in a lot, I'll show you some plots that sort of can bring that home. But in a lot of places, people who live along the freeways sort of breathe all the air that our cars pollute. And so that's, we want to be able to get around that kind of stuff, and we want to be able to have a economically sustainable transportation system. So how do we measure that, right? I mean, how could we come up with things that we could actually measure in terms of sustainability? I mean, we could talk about, for instance, in terms of society, things like the portion of transportation costs that are subsidized by the public. That's not necessarily a good thing. The amount of land area that we give over to transportation, there's all sorts of statistics that you can talk about, that like, in downtown Manhattan, what fraction of the land is actually given over to streets, right? It's like a lot. I mean, this is the most expensive piece of earth, and it's got these 4-lane streets that go down the middle of it. It's kind of crazy if you think about how much expense and how much land area we actually give over to transportation. Parking spaces, all that kind of stuff like that. These environmental things that we're used to, again, things like greenhouse gas emissions, things you might not think about, noise and noise is a really important part, for instance, of making it so that we can live in urban areas. And then, of course, cultural or equity-related stuff. We don't want to put people in a position where they're all paying the price for what is our convenience, right? So hopefully it's a little bit of a broader idea of what sustainable transportation might look like. Now, I'm going to take a second and you guys can look at this graph. It's kind of, I think it's actually one of a really, really interesting graphic and is informative. And so let's take a second and talk it over here, okay? So basically, on this side here, we have all of the different ways we use energy in the economy. Okay, so there are things here like residential, commercial, industrial, light-duty vehicles, freight, and aircraft. So this is transportation, industry, residential, and commercial energy consumption in the United States. This is all the sources of energy that we have in the United States. So for instance, petroleum, natural gas, coal, nuclear, solar, it's got a little flag on it. It's this tiny little yellow line here. Those renewable ones, geothermal, wind, are all these little spaghetti strips, as opposed to this like mega fire hose that is petroleum there. Can you see what's going on there? So for instance, what's the major source of energy into the transportation system? You can read it right off there, right? Petroleum, right? You see this fire hose of petroleum that comes in, and it goes right into transportation. The only part of transportation that's renewable is a little bit of well, so you can see a little natural gas goes into freight, and tiny bit of electricity goes into, there's electric trains and stuff like that that carry freight. There's a little bit of biofuels, biomass that comes into light duty vehicles, like the ethanol that we use as oxygenate in gasoline and stuff like that. But so this is what we want to do. We want to make transportation more sustainable, right? So we want to stop doing this, and we want to start doing something that is, these maybe, solar, wind, geo, biomass, hydro, something that's sustainable, right? I mean, that's renewable energy. So how do we get energy from those renewables into the transportation sector, right? There's a pretty weak connection between those right now. So you have, there's not that many choices, right? But one of them is definitely electricity, right? In fact, solar, wind, geothermal, hydro all make electricity. I mean, they don't make petroleum fuels out of those things, right? They all make electricity. So the question, so the challenge of renewable transportation is to say, what can we construct? What kind of a system can we construct to connect these little tiny spaghetti strings here and make a pathway so that it goes over here into light duty vehicles, right? It sort of illustrates the scope of the problem there, is that we have to, there's this much energy that goes into light duty vehicles. That's more than all of these combined, I mean, right now. No, that's exactly right. I mean, so I think that's a totally viable, that's a totally reasonable way to think about it, exactly, is that electricity, first of all, is one of the only ways that we have to get large volume, so electricity, you can see, the amount of electricity that we distribute and put to industrial, commercial, and residential sectors could make a pretty big dent in this light duty vehicle stuff, right? So it's not crazy. We already have a big energy infrastructure for electricity. It's sort of, I think it's reasonable to say we're going to power this stuff off of electricity. Now, the second thing you talked about it gets interesting as well, because when people talk about the ways that you can influence transportation, there's a couple different things that they would say. The first one is the energy source, right? So that's what I'm really talking about here. Where do the joules come from that are going to power this? The second way we talk about it is basically vehicle efficiency. That you can still have gasoline-powered cars, but if they drive twice as efficiently, then maybe that's really great, right? If they could double the fuel economy, that makes a big difference. That would make this pipe here go to half width. That might be really great too. But the third way that they talk about it is changing behavior and changing the way that we drive. And that's sort of what you're talking about, is if smart cars could change the way that we think about transportation, or if they could make the systems out here operate more efficiently so that they weren't stoplights. Everybody is sort of, so all those kind of, they're called intelligent transportation. They're called even that category also sort of embraces things that are like, car sharing or van pooling or whatever. Those things that are behavior changes and sort of changes to the way that we operate. Those are the other ways to do it. So you're on the right track, right? Because what you're proposing is things that have content in all three of those categories, and that's the way to make a big difference, right?
I think the thing that's most surprising the energy that we have.
Right. So what's for instance, like this is all. So transmission and distribution is relatively efficient. Most of that losses is due to the fact that we're burning something, and so we can only burn it at 30 or 40% efficient, and so that other 60% of the energy goes into heat, goes up the smokestack of the power plant or whatever, right? So that's what that means. And yeah, you can see, so again, in this case, for instance, that they break it out. This is by these guys at, I can't remember, one of the national labs. And basically they break it out into useful energy and lost energy. And you can see, even like the transportation sector here, is something, 3.4 of 17 is the useful energy, the actual, like, goods and services and stuff like that we get out of that. The rest of it is wasted, again. So there's this huge opportunity. I mean, there's definitely opportunity space in there. A small change in this efficiency has a huge impact on how much energy we actually get out of it.
And so you're also talking, with all of this hybrid aspect,
Mm-hmm.
of looking at the internal combustion engine and trying to make that more efficient and getting to those islands of efficiency that are higher up there. Is there any research on like secondary combustion chambers?
Definitely. So for instance, I mean, that's kind of the idea, in fact, of like the Miller cycle and Atkinson cycle stuff we talked about, is getting more efficiency out of the exhaust and more, so there are other sort of, I might call them less elegant ways to do that. I mean, it can be as simple as actually a turbocharger actually does the exact same thing. A turbocharger will get energy out of the exhaust and put it back into the engine. Even if you've ever seen old steam engines, they'll have what's called an extra expansion cylinder. That's a big cylinder the size of a barrel that you put the exhaust from the first cylinder in there into this barrel, and it gets more energy out. They're definitely, I mean, those sort of technologies are people are trying to do it, but it's just a question of how much gain can you get per buck. So anyway, I always think it's interesting to, again, like it sort of illustrates the scope of the problem here. If you thought about, for instance, let's say we had some miracle technology that tomorrow could make all of our vehicles run on coal, let's say, or whatever. I'm going to solve the petroleum problem for the United States tomorrow with my new coal-fired car. So we're going to get this, we're going to stop sending money to the Middle East. It's going to be great. Oh, darn it, we actually don't make enough coal to supply the light duty and freight vehicles in the United States. That's how much energy we're talking about.
Do you know how much, like over on the side where it's talking about the domestic and net import?
Yeah.
For coal, they don't have that, or like the enriched uranium, they don't have that either. Is that all domestic?
Yeah, basically, exactly. Yep. In the United States, almost 100% of our coal, I think we actually export coal, and uranium mining is done in the United States too.
But
So.
The interesting thing is, I think, and this where where lies the truth. When you look down at petroleum net imports and you look at natural gas net imports and stuff, especially in the petroleum, we've got major reserves
Mm-hmm.
that we're not tapping into because of, well, partially because of the environmental lobby,
Mm-hmm.
and who knows what other political forces say, no, we want to be tapped into the Saudis, we want to be tapped into there, so we have some control on what goes on or doesn't go on. And
So I hear you. And I think that part of the thing is that we're right now living in very interesting times on all these fronts. I mean, for instance, the natural gas production in the United States has skyrocketed over the last years. I mean, this was from 2007. So if you did this plot now, this would look much, much bigger. Petroleum would look much, much bigger. All these, probably everything's getting bigger, right? But the proportions of them are even changing all the time. So, the real answer is you have to think about this, as being dynamic as well in terms of time, and you never know. You never know what's going to happen. And all of the fracking that's going on in northern Colorado also has as a co-product from natural gas is petroleum. So it's also, it's sort of like we call it a co-product, but actually the petroleum has more value right now than the natural gas that they're getting out of there. So there's interconnections in between all these things. There's industries that are associated with them, and it's a dynamic picture. It's not to say that this is the slam dunk, that this is the slam dunk answer. Is we just got to all we got to do is steal all this electricity and start driving cars with it. But it gives you an idea of the kind of scope we're talking about.
yeah, I just think, ultimately it's a cultural, it's ethical, it's
Yeah.
all these things that students come out of the university should be carrying this kind of conversations that they
Yeah.
had in their heads, saying, well, we can learn the actual X's and O's and dynamics of how to make this thing work and to put this thing together, but
It's gotta function in context.
Issues
Yeah.
as to, do we want to do that, and what ramifications are we talking about when we go down that road, and how's that shift the cultural, look and swing of things, and who do we irritate and who do we don't? And
No, I hear you. All this stuff has to function within context, the context of the rest of the country, right? So, so we've got this. So, we sort of look at that and we say, gosh, why is transportation so unsustainable? Why is it that we don't, that we have all this petroleum fuel going in there? And there's a couple of answers, right? I mean, so for instance, we want to, so for instance, vehicles are a customer-oriented product, right? You sell them to customers, they're used by customers, they're often even maintained by customers. That actually puts a lot of demand on things like safety and all this kind of stuff. So for instance, we would like, methanol is a natural gas product that you could burn in engines. And it's not really a very big deal to do that, and we could do it. And there was a sort of a fad a couple decades ago where we were really interested in methanol as a fuel for cars, and it lowers pollution. It does all sorts of beautiful stuff. The problem is it's toxic to touch, and it's sort of like we could, you can design all sorts of safety systems. You can design all sorts of stuff to make it so people don't ever touch. But we all touch gasoline. I mean, it happens, right? It just happens. And it'd be really bad if every time we touch gasoline, every time you pull the thing out and there was that one little drip, that the sirens go off and the toxic waste crew comes in and whatever else and they clean it up. Or it'd be bad, right? So it's sort of like, in the same thing, we have to be really careful with electricity. We've got these big batteries, we've got these big things. Yeah, the first generation of electric plugs, actually, for electric cars, didn't even have electrical contact. It was a completely sealed system where the socket and the plug were completely sealed, like you could lick them and do whatever you wanted to do, and there was no way to electrocute yourself. And they were inductive, so they basically transmitted through a magnetic field. Now that was super inefficient. It was super expensive. It was a big pain. I mean, imagine how much more expensive that is than the plug that's right there, right? But they had to do it because if anybody were to hurt themselves on an electric car, that'd be the end of the industry, right? I mean, literally. So it's a real big problem. Personal transportation also has really high production scales. So we talked about tens of millions of cars sold in a year, and we would, for instance, everybody always says, and we would all love to see, for instance, carbon fiber or aerospace sort of technologies in cars. And if you compare the number of airplanes that that Boeing makes in a year versus the number of cars that GM sells in a year, they're 5 orders of magnitude different, or whatever it is. I mean, they're hugely, hugely different. So everything has to be cost driven. Everything has to be mass producible. If you go to a factory, I've been to the factory where they make Suburbans, GM Suburbans, and one rolls off the line, it's like every 50 seconds or something like that. So every process in the entire factory has to happen in less than 50 seconds, okay? So that means, and if it happens in more than 50 seconds, you have to have multiple lines doing the same process. So if something takes 2 minutes, you have to have 2 lines, one that sends one truck one way and one sends the other way, so that can sit on 2 lines and then join back up with the main line at 50 seconds per vehicle. So if they put on a tire, they've got one dude who puts on the tire, and that takes 30 seconds to do to get it right and aligned and everything. And they have another dude with a gun that's got 6 wrenches on it, and he goes woo, and tightens all 6 at once, because to tighten them once at a time would take more than 50 seconds, et cetera, et cetera, et cetera. So imagine if you were trying to mold a part that took, a carbon fiber part that took 4 hours to cure, how many parallel lines are you going to have? I mean, it'd be impossible, right? So everything has to be mass producible. Everything has to operate at this mega scale. we've talked about, that storing energy is really hard. The renewable energy, sort of it operates at a different scale than automotive systems. So I sort of jokingly say you can't put an anaerobic digester on a car, which is a type of way to make methane from things like agricultural waste and stuff like that. But also infrastructure is a real problem. One of the most important things, and something that I think you exactly pick up on, is that the societal and personal hierarchy of needs is really important here, right? We all make decisions every day about how sustainable we want our world to be. And for instance, if I was king of the world and I had to allocate energy and money and whatever else to things, maybe, and it was a finite resource like the amount of petroleum that we have in the United States is, right? Maybe what you would say is the most important thing that we can do with our petroleum is defense, right? Maybe the second most important thing is agriculture, right? We need to feed ourselves. Maybe third is mass transit. Fourth is long-range travel. Fifth is personal travel. Maybe sixth is that guy at the campground who's idling his engine so he can run his radio and blast music in the campground or whatever. That guy's burning petroleum too, but that would be low on my priority list if I was king of the world, right?
You'd be that guy.
But that guy, his priorities are reversed, right? I mean, and it's not that guy, it's us. We all drive for personal travel. We all drive for long-term travel. We all do this sort of stuff, right? And so it's you can't blame the guy. It's all of us. And so that's the thing is there's this, it's about doing what we want to do. Our personal hierarchy of needs might be different than the societal hierarchy of needs, and there's nothing to be done to get around that. That's perfectly fine. But it's why this isn't very sustainable, right? Now, so what we want to think about a lot here, we can talk a little bit about this, but mass transit in general can have pretty high, can have pretty low energy consumption, high fuel economy. So, for instance, commuter rail, which is a heavy commuter rail, would be like BART in San Francisco, or not like a streetcar or whatever, but real rail. It gets something like several hundred AC watt hours per person per mile, and a EV gets about the same order of magnitude, right? So you could drive an EV and you'd be a super environmental guy or whatever, or you could take the BART to work and get about the same benefit. For instance, a 747 gets about 70 miles per gallon per passenger. So it's sort of like, it's not, per passenger per mile, it's not terrible. I mean, right? I mean, it's not that bad.
But it's more like 3 gallons per mile. Just
in real world, yeah. I mean, so right, and God forbid it flies half full or something like that, right? Then it'd be half of that or whatever. I mean, or if you were just driving one person. I mean, it seems like really bad, except for that a 747 is full of 300 people or
Will you
whatever.
comment on that commercial that was out a while for the train? It was like 500 tons of freight, 500 miles on a gallon of fuel. Does
Yeah.
that really work out?
Yeah, that's it. It's pretty close to that. I mean, I think I read that that's sort of, that's a generous estimation of fuel economy of a freight train, but yeah.
And all those costs are passed on to the consumer, right, onto the
Yeah.
ultimate product.
Sure.
So if we ultimately come up with that device, the power
That can-
pulls out of the void, where then they don't have to levy that cost onto the product, then you see consumers saving money because that dollar amount doesn't have to be passed on to the consumer.
Yeah.
They can now use their money to do other stuff.
It's less waste, yeah, exactly. So the thing is, again, like part of the thing is we want a way to compare, for instance, so this is an EV. We want a way to compare the environmental or sustainability sort of impact of an electric vehicle that has units of 290 watt hours per mile, which is pretty. I mean, I would understand if that doesn't mean anything to anybody, right? Versus what this would be if it was a conventional car, which is maybe 25 miles per gallon or something like that. How do we compare those, right?
What's the AC stand for?
Alternating current.
Oh, okay.
Alternating current versus DC. So it's basically, I just applied an efficiency of charging to that. Yeah. You know, so how are we going to figure that out, right? How do we do that? Well, the answer is sort of we have a technique to do that, and it's called full fuel cycle analysis or life cycle assessment. Okay, and the idea is, you know, we've got a car here, okay, and this is from the National Lab, and we got a car, and how much energy? So, you know, the question is, how much energy goes into this car over its lifetime, from being a brand new car to being a recycled junker or whatever, right? Well, there's a couple different ways that we can think about that. The first one is, well, so there's a couple of different inputs of energy. The first one, let's say, is the amount of energy that it takes to build the car, that it takes to make the materials, to assemble it, to sell it, and to put it in your hands, right? That takes some amount of energy. The other part is that it takes some amount of energy to make the fuel that fuels the car, right? There's
As well as all of the materials
that it takes.
used, just getting them,
Yeah.
to do them, and to ultimately put them up to start making them.
Yeah, so this is like, for instance, steel, like steel or rubber or plastics or adhesives or anything that it takes to make the car. This is stuff like exploration, refining, transportation, distribution, pumping, whatever else, right? And then there's the energy that is actually used by the car, right? I mean, so like there's a certain amount of of joules of energy of gasoline that the car uses. So we have ways, actually, and this is sort of part of the research that we do here, is trying to figure out how do we make these comparisons between electric cars and conventional cars? Which is better? Which is worse? How do we stack these guys up? So for instance, you know, this is just an example. Like, we want to compare, everybody knows about like ethanol E85 cars and stuff like that, right? So it's like, so if you buy any Ford vehicle, or actually it's a Ford truck now or whatever, it has a sensor in it that you can run it on either E85 or gasoline. And so you say to yourself, all right, I'm at the gas station, one pump is E85, one pump is gasoline. I want to do an environmentally friendly thing today. What should I do? You know, should I fill up with gasoline or should I fill up with ethanol?
Park it.
I'll say exactly.
Yeah, take that bicycle out of the back of it.
Yep. So that's the question is what to do. How do we figure that out? Well, what this does is it basically, this technique is a sort of an accounting technique that accounts for all the energy inputs that it takes to generate 1 million BTUs, which is a unit of energy of ethanol at the refueling station, or 1 million BTUs of gasoline at the refueling station. And if you do this calculation the way that this national lab did it, you find that it actually takes 0.78 million BTUs of fossil energy input to make 1 million BTUs of ethanol. So let's sort of think about that, right? That means that I just put in 0.78, I put it a million BTUs of energy, I put it through this process that involved the sun shining on corn, refining corn, transporting it, doing all these kind of things like that, making ethanol, and I got out 1 million BTUs of energy. So what it basically did is it captured this solar energy to the tune of a couple of percent, of 20% or whatever, and put it into your ethanol. Right?
Yeah.
Sort of follow that?
Well, wait a minute. You got to produce 1 million BTUs, right?
Yeah.
So on the scale, that's 1 million.
Yep.
But if you went down the scale, you got to go down the scale 7.78 first and then come back up. So the difference is between 7 million and 1 million. That's your win.
Right, and so for instance, yeah, that's you got it exactly right. So for instance, like let's say I've got 1 million BTUs that comes out of this thing, and I have a couple of inputs. We're going to call this ethanol process box, not to be too specific here, right? But there's a couple of things that go in. The first thing that goes in is some amount of fossil fuels. For instance, gasoline to drive this truck that's moving stuff around, electricity to heat the refining. Yeah.
I kind of know what a BTU is, but can you drive a car on the same distance on 1 million BTUs of ethanol that you can on 1 million BTUs of
Yeah. I mean, pretty close.
Because I've heard it takes more, like ethanol's less efficient, and it takes more of it to go the same distance.
That's per unit of volume. So ethanol has a lower heating value, BTUs per gallon, than gasoline does. So you would get, if you fill up your gas tank with ethanol, you'll get lower miles per gallon, but your energetic efficiency will be approximately the same.
Well, you have a slide with what's the cost, dollar cost to produce that 1 million BTUs in relation to the cost of the.
Yeah, so you have to go to the station and ask them, right? But it's comparable. It's comparable. This metric that I presented here is really all about energy, right? And are we getting more energy than we put in, or whatever, right? And what you guys are saying is that, oh wait a minute, there's got to be more considerations than that. We got to think about water. We got to think about air pollution. We got to think about economics. We got to think about all that other stuff that makes a sustainable system. And that's exactly right on. Right. Yeah. So again in this. No, so the idea is that we're not talking about stuff at geologic scales here or whatever. We're not talking about stuff that happened 60 million years ago. We're talking about stuff that, I mean, the idea is to try to make a decision here, right? We can't help what happened 60 million years ago. We're trying to make a decision about which one to fill our tank with, right? And that's obviously that's sort of like the purpose of analysis like these, is to say, what's the right thing to do? What can we actually do defensively that would be more or less sustainable, right?
Yeah, I'm asking why is the ethanol more?
Let's put petro here, right? And again, we get out 1 million BTUs, and we put in 1.23 million BTUs. So this one kind of makes sense to us, I think, right? Because you got to, nothing comes for free. There's no other source of energy and stuff, right? It takes energy to refine crude oil into petroleum, and so I think we should be comfortable with sort of the progression here, that it takes more energy, that converting from crude oil to gasoline takes energy, 0.23 million BTUs more per million BTUs.
Two things that I think would be interesting for this.
It's a really good point. The thing you talked about right there is this other petroleum products right there. And those are what's called co-products, okay? And those are things that are also produced as a sort of call it a side effect of producing gasoline. We also produce, asphalt and kerosene and whatever, all kinds of things, right? And in the same way, we actually produce animal feed from ethanol. So so the idea is, like an accountant, you kind of have to come up with some amount of that energy that's allocated to this part, and some amount of that energy that's allocated to this part, and some of that energy. And there's a sort of an art to doing that, and there's some rules of thumb. It's a really good point. And basically, what we do in these kind of studies is we try to make assumptions that are as defensible as possible. It's hard to do.